Welcome to this video lecture where the inverse Laplace transform is defined and some important properties of the Laplace transform are also introduced. So let's start with the Laplace transform. As we saw in the previous video lecture, the Laplace transform is a transform that uses as an input a function in the time domain and that gives us an output that is a function in a different domain that normally is called the frequency or the Laplace domain. Now, we know how to go in this direction. We know how to, from a function that depends on time, we know how to go in this direction and compute f of s. In fact, we did that for some very basic functions as the constant function 1, t, and so on. Now, the point is that there is also the way back. So we can really go backwards, and that is called the inverse Laplace transform. That means to take a function on the frequency domain and assign to it a function that depends on time. Now, remember, this is very important. We have already seen in the previous video lecture that two different functions in time can have the same Laplace transform. We saw that the constant function 1 and the step function at the origin have the same Laplace transform because they are exactly the same from 0 to infinity. So when we compute the inverse Laplace transform, we must be very careful because, of course, there are plenty of solutions here, but don't be scared. All of them are almost the same from 0 to infinity. So for t greater than 0, this function f of t can only differ punctually at some points, but they will be very, very similar. Okay? So this is a concept, the inverse Laplace transform, that we will see in a few slides, that we can also go backwards, but instead of using a definition, like here for the Laplace transform, that we have a definition with an improper integral and we do some algebraic calculations, here to go backwards, we will use a lot what are the Laplace properties. So first, let me introduce some of these properties. Here in this table, I have summarized the most important Laplace transform properties. We will in this course explain each one of them point by point, so that don't be scared. This is just a summary. Today, right now, we will do the first one that is called linearity. So let's start with that one. The linearity of the Laplace transform means that when we have two functions f and g of t that we can compute its Laplace transform, then any linear combination of these two functions has as Laplace transform the linear combination of the Laplace transform of f and g. I think that this notation is much easier in this case, okay? This notation of the arrow is telling us that when f of t and g of t are functions that have a Laplace transform, they are admissible, then the Laplace transform of these, where a and b are just real numbers, the Laplace transform of this is just a times the Laplace transform of f plus b times the Laplace transform of g. This is the linearity property, and it's pretty simple to prove, and it's just inherited from the linearity of the integral operator. The integral operator is linear. That means that constant values can be written outside, and that the sum of two functions can be split into two integrals. So basically, the linearity of the Laplace transform is inherited from the linearity of the integral operator, because the Laplace transform is nothing else but an integral. Okay? So this is a very important property, linearity, and here we have a very easy example. Let's consider I want to compute the Laplace transform of this function. Okay? If I want to compute this Laplace transform, I'm going to write that I want to compute the Laplace transform of 2 times the exponential minus the sinus of t. Okay, now by linearity, I know that, now this is like a, and minus 1 times the sinus, this is like b, and I know that this is equal to 2 times the Laplace transform of the exponential minus 1 time the Laplace transform of the sinus function. So I just need to go to the table of the Laplace transform, check which is the Laplace transform for the exponential and from the sinus function, which we have here a summary of this Laplace transform basic table, and just use that here. Okay, so the Laplace transform of the exponential is 1 over s minus a. So here I will get, using the table, that this is 1 over s minus 5. And for the sinus function, the Laplace transform is this guy. In my problem here, omega is 1. So what we will get for the Laplace transform of the sinus function is that this is 1 over s squared plus 1 squared, which is 1. So basically what we will get is 2 times, oh, sorry about that, 2 times, which is here, 2 times this term, which is here, and minus this term that was here, okay? So this term that was here. So linearity is a very easy to apply property. Now, another property that is very important is the complex or Sshift. That is a translation in the frequency domain. And the property looks like this. The Laplace transform of the exponential, an exponential function times f, is equal to just translation in the frequency domain. So when in time domain I multiply by an exponential, what I get in the frequency domain is just a translation of distance a of the Laplace transform. So this property is very easy to prove. We will just use the definition of the Laplace transform, and we will plug this function that we want to compute its Laplace transform here, okay? And this will be multiplied by the exponential of minus st. And arranging terms, we will get this thing. So this is a very important property that we will use a lot when solving differential equations. So it's very important that you know that multiplying by the exponential function in the time domain relates into the frequency domain to just do a translation of distance a. Okay? It is very important when you read these slides that you understand that we are meaning that the Laplace transform of small case f is capital F of s. So I'm assuming that you understand that the Laplace transform of f of t is capital F of s, and that the Laplace transform of this whole thing is this whole thing, which is not exactly f of s, but is the translation of f of s, a distance a. Okay, this is another very important property, which is translation in frequency. Now, you have some examples here that you can try to do it by yourself at home and try to compute the Laplace transform of an exponential times the cosinus, function, for example. Okay? Now, to end this video lecture, we will talk about the inverse Laplace transform for rational functions. We already know what is the inverse Laplace transform, but as I said, we don't know how to go backwards. We really don't know exactly how to compute the inverse Laplace transform. Now we will see here how to do it for a specific type of function that appears a lot when you want to compute the inverse Laplace transforms, which are rational functions. Okay, so for example, what if I want to compute the inverse Laplace transform of this function, 1 over s to the power 5? Well, of course, I will have my table of Laplace transforms. Let me go backwards. Here, for example, we know that the Laplace transform of t to the power n is n factorial divided by s to the power n plus 1, yeah? So we can use this here. And we know, I will just copy it here, I know that in our table, when f of t is t to the power n, its Laplace transform is n factorial over s to the power n plus 1. Now, they are asking us, can you compute the inverse Laplace transform of this function? What I do to compute this is always to try to find in the table something that looks pretty similar to 1 over s to the power 5. And this is pretty similar. You see, if I write here s to the power 5, that means that n is equal to 4, yeah? So if I have 4 factorial here, let me write that 4 factorial, okay? If I have here 4 factorial divided s to the power 5, all of you will agree that this is the Laplace transform of the function t to the power 4, yeah? But now some of you are very worried because, wait, I don't want to compute the Laplace transform of this function. I want to compute the Laplace transform of 1 over s to the power 5, and you don't have a 1 here, you have 4 factorial. Okay, let's arrange that. That's very simple because the Laplace transform and the inverse Laplace transform, they are both linear. So both the Laplace transform and the inverse Laplace transform are linear. So if they are linear, I can multiply by a constant value here, and in the time domain, it will get multiplied by the same constant. I can multiply this by a, and this will be multiplied by a. That's the meaning of linearity when dealing with a constant value, yeah? So the question here is, what value of a should I use? What value of a would be great to use here? Maybe 1 over 4 factorial will do the work, because if I multiply by 1 over 4 factorial, this 4 factorial eliminates with this one here, okay? And I get the function 1 over s to the power 5, which was the function I wanted to compute the inverse Laplace transform. So the solution is this one, which is what you have here in the slides, okay? You have other inverse Laplace transforms here. You can try to do it following the same idea, like this one here, okay? And this one here also, the idea is to try to rewrite it in such a way that you get functions here that appear in the table of Laplace transforms. Finally, sometimes it can be a little bit more complicated because the function that is given to you does not appear in a clear way in the Laplace transforms table. When that happens, like in this specific case here, we need to rewrite things in such a way that we can use the table. And when we have rational functions like here, this is rational polynomial functions. Normally, we will see in future video lecture, but in general, the way to proceed is to do partial fraction decomposition and rewrite the polynomial, the rational polynomial, rewrite it in this decomposed form, and then it will be pretty easy to just look into the basic Laplace transforms. Here we have this rational polynomial. As they are simple roots in the denominator, we will decompose it using this structure, okay? And we will find the value of A, the value of B. You can check your notes of Calculus 1 to do that. And when you do so, you will find the value of A, which will be 1 over 4, and you will find the value of B, which will be 3 over 4. And then, as the inverse Laplace transform is linear, this 1 over 4 can be written outside, and the 3 over 4 can be written outside from the inverse Laplace transform. And now you have to compute the inverse Laplace transform of things that already appear in the basic Laplace transform table. If you check it out, you will see that when you have the exponential of AT, its Laplace transform is 1 over S minus A. So you can just check into the Laplace transforms table, and when A is equal to 1, this is the exponential of t, and when A is equal to minus 3, okay, then you get here the exponential of minus 3t. You have here another example that you can try to solve, but it's the same idea to rewrite it well, here you need to check it out. Here it really uses a translation over S, okay, to rewrite it in a way where you can just use the Laplace transform table of polynomials, okay? So try to do it at home. That's what I wanted to cover today. See you in the next lecture. Bye-bye.